Now that we've gotten good at proving existence statements, we're going to move on to disproving existence statements. Now, there's nothing new in the material we're going to talk about today. We're just putting together a couple of ideas from the past. So, firstly, when we disprove a statement, we're really proving its negation. So, if I have an existence statement, there exists x and s such that r of x. Now, the negation of that statement, I'm negating an existential quantifier, which if we reach way back, we know that that means that the negation of the existential quantifier is going to become a universal quantifier. So not there exists x in s, r of x is going to become for all x in s. And then we pull the negation into the statement, so not r of x. So these statements, these universally quantified statements, this is what we've been proving with all of the proofs that we've done so far. So the proofs today are going to look more like the proofs before we were proving existence statements. And so we're really wrapping back around to that. It's just a matter of negating the existential quantifier and to negate the existence statement before we have our statement to prove. So let's take a look at a couple of examples. So we're asked to disprove the statement, there exists an odd integer n such that n squared plus 2n plus 3 is odd. Now, whether or not we were told to disprove this, you might be in your head going, I don't know that I can do that. I don't know that there is an odd integer. And if you were trying to convince yourself that there actually is one, you might let n be a generic odd integer. And that's exactly what we're going to do to start our proof of the negation. So we have n is an odd integer, then n squared plus 2n plus 3 is even. That's what we want to prove. So we're going to let n be some generic odd integer, 2k plus 1 for an integer k. So we have n squared plus 2n plus 3 equals, and we're going to plug in our 2k plus 1 and for n, and we're going to simplify everything, and we're going to get to the point where we have 2 times the quantity 2k squared plus 4k plus 3. Now, that quantity is an integer, so our original statement, n squared plus 2n plus 3, is even by the definition of an even integer. So here's another example. There's a real number x such that x to the 6th plus 2x to the 4th plus x squared plus 2 equals 0. Now, hopefully, fairly quickly in your head, you're going, that doesn't work. And if you are, you're right. All right, so we're going to take any generic real number, x. Well, when I take a real number to an even power, like x to the 4th, x to the 6th, x squared, all of those are going to be greater than or equal to 0, depending on my real number. But positive numbers, at least 0. So if I plug in 0 for x to the 6th, x to the 4th, and x squared, I know that x to the 6th plus 2x to the 4th plus x squared plus 2 is going to be greater than or equal to the result. Well, the result when I plug 0 in is 2. So that means that x to the 6th plus 2x to the 4th plus x squared plus 2 is greater than or equal to 2. So it cannot possibly be 0. So I've disproved that statement. Here's a final example. There exists an integer n such that n cubed minus n plus 1 is even. Well, the negation of this that I want to prove is for all integers n, n cubed minus n plus 1 is odd. Well, for all integers, remember when we had statements like that before, we liked to break it into a case of even and odd when we wanted to make some kind of statement about whether it was even and odd. And that's exactly what we're going to do. So integers can be either even or odd. So I'm going to first consider when n is even as case 1. So n equals 2a for some a in the integers. And when I substitute in 2a for n, and I do all this arithmetic simplification, I end up with 2 times the quantity 4a cubed minus a plus 1. Now, 4a cubed minus a is an integer, so therefore, n cubed minus n plus 1 is odd by the definition of odd. Now I need to consider the case where n is odd. So again, I write n as a generic odd number, 2b plus 1, where b is an integer. I substitute that n for n, and I do some arithmetic, some simplification, and I get 2 times the quantity 4b cubed plus 6b squared plus 2b plus 1. Now 4b cubed plus 6b squared plus 2b is an integer, so by the definition of odd, n cubed minus n plus 1 is odd. Therefore, since both of these cases turned out that n cubed minus n plus 1 was odd, then for all integers n cubed minus n plus 1 is odd. And I've disproved the existence statement.